In this video, we explore K-means clustering using multilayer perceptron MLP in C++. Let's first have an overview of this topic. We have discussed K-means clustering before. It is a unsupervised learning algorithm. We have also discussed multilayer perceptron MLP. It is a supervised learning process. K-means NLP is to combine these two processes. In this method, we first find clusters of a large data set using K-means clustering. Then we train the MLP using the data set and the centroids found from the clustering method. Then the trained MLP can be used to find clusters of new data. The advantages of this hybrid method is that we only need to train the MLP once. And the MLP can then be used to classify new data efficiently. We don't have to go through the calculations of clustering again. Here are some example applications. One is EEG signal classification. In this application, K-means can be used to cluster wavelet coefficients of EEG signals. And then an MLP is trained to classify the signals using the cluster probabilities. And it can also be used to classify new data. Another example is geological model inversion. In geophysics, K-means clustering can be used to cluster the one-dimensional data, such as ATEM responses. Then an NLP is used to map this cluster to geological model types. And this can be done efficiently. Let's have a brief review on K-means clustering and multilayer perceptron, MLP. We discussed K-means clustering at this website. So here's the algorithm of K-means clustering. So first, we randomly pick K central points called centroids or means. Each data point is assigned to the closest centroid. Thus, we have K clusters. So we have unlabeled data. So the K-means clustering will obtain K labeled clusters. Okay, the records here is a centroid. Okay. Then we update the centroids by finding the average position of each cluster. And we iterate the process for a number of times until the clusters become stable. Okay. So this is the K-means clustering algorithm that we discussed before. And here's the C++ implementation. We also have discussed this before. Now let's copy these programs again. Now we first copy the header K-means.h. Okay, so we copy this Kmeans.h. Okay, so we paste this into this file. Okay. And we save it. So we have this, and let us copy this Kmeans.cpp, the implementation of the Kmeans clustering function. It is straightforward. So we copy it. So this is Kmeans.cpp. I paste it, save it, so you can see that we can compile this. Okay, so we get this object file kmeans.o. Okay. The implementation is straightforward. We discussed this before. So we define the struct point with double xy and in cluster. So this the function Kmeans. We pass in a vector points and centroids and the number of iterations. And here's the implementation. So the function distance calculates the distance between a point from a centroid C. Okay, straightforward. And this Kmeans function is to cluster the points to associate with the nearest centroid. And again, the implementation is straightforward. And we compute the centroids, taking the average of the points in the cluster. So this is straightforward. So this is the Kmeans clustering we discussed before. Now let's review the multi-layer perceptron, MLP, which can be found at this site. Now, this is the site that discusses multi-layer perceptron. So we discussed the principles of MLP. Okay. Basically, an MLP consists of an input layer, okay, one or more hidden layers, and an output layer. It is a kind of supervised learning. Now, here's the MLP with backpropagation algorithm. Okay. And these are the notations that we use. So we have inputs x1, x2, blah, blah, to xn as shown in this diagram. Okay, x1 to xn. And the hidden nodes are denoted by h1, h2 to hm. Okay, h1 to hm. And the outputs are y1, y2, blah, blah, up to yk. Okay, as shown here, y1, y2 up to yk. Okay. And the neurons are connected by ways. Okay. So we have a way matrix from the input to hidden, and a matrix from hidden to output. And we'll use an activation function, which is a sigma function given by this formula 1/1 per c to the power minus c, sigma c. Okay. So this is the sigma function. And the derivative of a sigma function is given by sigma c times 1 minus sigma c, okay, shown in this curve. And the ways wij will be the weight from input xi to a hidden node hj. Say from this node to this node. Okay, so that's the weight of the ij. And wjl is the weight from hidden node hj to open node yl. Okay, for example, from here to here. Okay, and in the forward propagation state, we compute the output of the network from inputs. So in step 1, we compute hidden layer activations. That means from here to here. Okay, and first, each new one compute this aj, each of this each new one. Okay, compute aj according to this formula, sum over I from 0 to n wij xi, j equals 1 to m. Okay. And in here, x0 will be our bias, which is equal to 1. Okay. And w0j is the bias. Okay. And then each new one will compute, okay, hj given by g aj. Okay, aj is this hj, okay, and g is the activation function sigma here. Okay, the sigma. So that's the first step. And then in step 2, we compute the output layer activation from the hidden layer. That means from here to here. Okay, and the formulas are similar. So first we compute CL. Okay, so the input to each output node. Okay, from j equals 0 to m, some JL. O here means output xj. Say each of this value, okay, is fed into one node. Okay, say node L. Okay, and then we have to sum over all these values. Okay, each of these values is fed into this one of these output nodes. Okay, and then after we compute the CL, again we put that in the activation function to calculate the output YL. Okay, so this is the final output. So in the formula again, H0 is the bias, it is equal to 1. So W0L, okay, is the bias. The O here means output. Okay. Then after we have computed these Y values, we have to compare with the target output, okay, or the desired output. So we calculate the error. Okay, that's done in the back propagation stage. Okay. So the error EL is equal to YLDD means desired, okay, the desired output, minus YL, the one that we calculate using the network, the MLP. And then we calculate the gradient of the output error using this formula that we discussed last time. EL is delta L. The gradient is equal to this error times the derivative of the activation function. Okay, so G dash here is equal to partial G partial CL. Okay, and then we compute the hidden layer gradient error using this formula. Delta J equals sum from L equals 1 to K delta L times WJL O times G dash AJ. Okay. So we have delta L, delta J. Okay. And then using this, we adjust the weights. Okay. We adjust the ways from hidden to output layers using the delta L here, the output error delta L. So the WJLO is equal to the original WJLO plus eta is the learning rate times delta L calculated here, times HJ. So HJ, the value at the neuron, calculated from here. And then we also adjust the ways from input to hidden layer using the delta J here. And so the implementation of these formulas is straightforward. So this is the code we discussed before, the implementation of these formulas. A straightforward implementation. Let's go back to our site. So we just had a brief review of Kmeans clustering and MLP. And this is the diagram we just discussed, showing an MLP with n inputs and m hidden nodes and k outputs. Now, this is a straightforward implementation of the formulas that we just discussed. This is the header file. Let's copy and paste this header file. So we got this MLP.h. So we paste this. So here in our model, our N1 is 3, which is the number of inputs per bias. So basically, N is equal to 2, two inputs and 1 bias. And M1 is 7. So again, the number of hidden nodes plus the bias. So M actually is 6, and K is the number of outputs, that's 4. In here, it is equal to the number of clusters. So this is the MLP class, the prototype. So here we hard code the N1, M1, and K. Now the programs we present here are mainly for explaining some basic concepts. It might not be efficient or elegant. So for example, in practice, you may pass these parameters to a constructor of the class, and use vectors instead of arrays or dynamic memory allocations. But here, it's just for convenience. We do this to explain how this can be done. So we save this and quit. And here's the code, MLP.cp. It implements everything we just discussed. So this is the constructor with the learning rate, we call it eta before. So H0 is 1, that's the bias. And we start with random ways, so between 0 and 1. And so that this is from the input to the hidden. So this ways, the W. And WOJL, is from here to here, okay, from hidden to output layer. Again, we start with random values between 0 and 1. Okay. So JL, okay, L from 0 to K, and J from 0 to M1. Okay. And remember, X0 is the bias, X0 is also the bias. Okay, they are equal to 1. And this is the sigmoid activation function, 1 over 1 plus exponent minus x. Okay, and this is the derivative of the sigmoid function. Okay, so s equal to gx, and then the derivative is s times 1 minus s. Okay. And this is the function of forward propagation. Okay. The strict implementation of the AJ we just discussed, okay. Sum over the Wij times Xj, okay. And then Hj is equal to G, the sigma function, okay, Aj, okay. And H0 is 1, the bias, and this is the output layer. Okay, we just mentioned. Okay. So again, we just sum over WJL times HJ. Okay. And then YL is the activation function of ZL. Okay. And then we return Y, that's the output. Okay, is the pointer to the array. And this is the backward propagation. So remember, we have the delta and delta O for output. Okay. So remember we calculate the error, the YDL minus YL. Okay, the error, and then the delta L. Okay, is this E times the derivative of the CL, okay, we just mentioned. Okay. And also delta J, okay, is the sum of this. Okay, so it is the implementation of this formula, strict implementation. Okay, nothing special. And then here we train the perceptron. Okay, eta is the learning rate, apples is the number of times of training, lump sample is the number of different input sets. Okay, well, there's no X data here. I copied this from the old program. Okay, we don't use it here. YD is the target output. Okay, so this is the training routine. Okay. We pass in the points, the vector. Okay. Actually, something missing here. Okay, I'm gonna fix this. Sorry, there was a mistake. We missed the point here, and we just corrected it. We also missed the point in the header file, and we also just corrected it. Okay. Now in the train function, we train for that many times, apples times, okay. And for each time we go through all the sample points, okay, which could be 1,000. Okay. And for each point, okay, we have 2 coordinates, x, y. Okay, so here our inputs to the MLP, to the perceptron, okay, are x1, x2. That means we have 2 inputs. x1 is the x coordinate of the point, x2 is the y-coordinate of the point, and of course x0 is 1, which is the for the bias. Okay. Then we input this for the forward iteration, okay, forward propagation. Okay. And now after that, we need to check, okay, the corresponding target output. Okay. For the outputs, the number of outputs is 4. Okay, the same as the k value. The k value we selected is 4. Okay. So if the points cluster is equal to one of those numbers, say I, then we set the target to be 1. Okay. Otherwise, it is 0. Okay. And then we do the backward propagation with these targeted values. Okay. So we iterate through this. And this is the destructor. Okay. Now let's copy this and try to compile it. We copy this. And call this MLP.cpp. Paste it and save it. So this is the program we just copied. Okay, and now let's try to compile it. Okay. G++ minus C MLP.cpp. So it compiles, so there's no error. Okay. So now we have these object files. This program is for testing Kmeans MLP. We define screen width and screen height to be 700 and 600 respectively, as we'll use both text and graphics interface. So this routine graphics is for graphics interface. The function classifier is to classify the output Y, whether it is in the cluster region 0, 1, 2, or 3. Okay. So we know that. Okay. So if it is in, say, region 1, then Y1 should be 1 and other should be 0. So that's why we just take the maximum value. Okay. Overlap function is to ensure that the initial centroids won't overlap. So this is the use MLP routine. So we use the MLP that we created, and we pass in the points in these vector points, and delta is the increment or separation that will print out the results. Okay. So we print out the results to make a demonstration. So here x1 is x, okay. X2 is y, okay. And then we get the output from the forward function, okay. And we print out the predicted value. We classify the output first, of course, right? And then print out the values. And now, so here's the demo. We create an object MLP with learning rate 0.5, okay. And also we create a centroid vector with k values, and the number of samples we'll use is 900, okay, and iteration is 15. That's the number of Kmeans iterations. So we create a vector of points, totally 900, and we use the random number generator to generate random values and normalized the xy values to be between 0 and 1. Okay. And then put this in the points vector. Okay. So the points is here, these points. And we randomly initialize centroids from the points. And again, we use the overlap function to ensure that centroids don't overlap. Okay. Then we call Kmeans with the iterations to classify, to cluster the points, okay, and find the centroids. So the centroids are returned in these vector centroids. Okay. And then we print out some values, some point values, and also the centroids, what the clusters it belongs to. So we don't print out all the points, otherwise there will be too many. We just print out a certain number of points, so we increment j by delta. And so this information is for comparison. So now, after we have all the clusters for the points and the centroids, we train the MLP using the points and train that for 10,000 times. Okay. And then we use MLP that function to obtain the clusters. Okay. Use MLP here, okay, and print out the examples. Okay. And we compare the two cases to make sure that they are the same. Okay. And the care is to give a pause. So when we hit enter, then it will continue to execute graphics. Okay. For the graphics, we just use graphics routine interface. So this is the usual graphics initialization using OpenGL. Okay. So the screen is size is screen width, screen height. Okay. And draw dot is to draw one dot. Okay. And the routine display cluster is to display the clusters of the points, okay, in this vector points. And we use different colors, so for different clusters. So we use red, green, blue. Okay, the fourth color is black. Okay. So depending on the cluster number. Okay. And then we draw the dot, okay, to show using a color to show which cluster that point belongs to. We also display the centroids, and we use a large point size, 9. Okay? And the color for a centroid is magenta, okay, 101. Okay? So this is for the centroids. Again, because everything is normalized between 0 and 1, so we need to multiply these values back with screen width and screen height. Okay. Then we restore the black color and the point size 3. This is the keyboard. When we press the key D, we display the clusters. Okay, display this. Okay, or the clustered points and the centroids. Okay, and M is to use the MLP. That means we will print out the clusters. Okay, use MLP. Okay, this one, to print out the clusters and the centroids. and the points are saved in point vet. Okay, we put the points in point vet by clicking the mouse. Okay, using this routine. When we click the mouse, okay, we draw a dot xy, and we create a point. Okay, again we normalize that to 0 and 1, and put this point into this vector point vec, okay, which will be passed to use MLP to do the MLP classification. So this is the graphics routine. Okay, so graphics routine. These are callback functions. Okay. Now let's copy this. So we copy this. And so this is test k mlp.cpp. Paste. So save it. Okay, and then compile g++ -c test kmlp. So again it compiles. So we got this object file. Here are some sample outputs. Okay, so you can see that these are outputs from the Kmeans clustering. Okay, so these points are clustered to these cluster numbers 0, 3, 1, 0, okay, 3, 2, 3, 1, okay, and these are clustered by the MLP. Okay, so again you can see we have the same result: 0, 3, 1, 0, okay, and then 3, 2, 3, 1, okay, so on. For the last is 2, 3, 3, 1, 2, 3, 3, 1. Okay, so this is the point. Okay, and now this is the Y output. As you can see, this, okay, say Y0, if it is 1, then that means that the cluster number is 0. Okay. And for this point, when Y3 is 1, okay, then the cluster number is 3. Okay. And so for this, okay, Y1 is 1, then the cluster number is 1. And for this, Y0 is 1, so the cluster number is 0, okay, and so on. Okay. And these are the graphics outputs. Okay. So these are the centroids, and these are the clustered points. Okay. Red, green, blue. This is red, green, blue, and black. Okay, these are the centroids. Okay. Now let's compile and execute the program. Sometimes it is easier to use a makefile, okay, to do this. By the way, I forgot to mention this. In the function use MLP, this statement MLP.forward x will give us the predicted output. Okay. And then this statement classifier output will give us the actual cluster number. Okay. And we assign this to the point I.cluster. So that means we cluster the point to the correct cluster number. And this is the makefile. Yeah, we have copied this makefile already. Now this is the makefile we just copied. Okay. Now make sure that you use tab here. Okay. So now we can type make. Okay. So it creates this executable test KMLP. Now we can execute this. So this is from the Kmeans cut string. So it cuts the points. And this is from the MLP. So you can compare the results. So these points, okay, are clustered into 0, 1, 2, 1, 0, 1, 2, 1. So they're the same. And then 3, 0, 2, 1. 3, 0, 2, 1, so they are the same. That means the MLP does the right job. And so at the bottom it is 3, 3, 3, 1, 3, 3, 3, 1. Okay. And again, as you can see it, when you have a 1 here for the Y output, okay, so that means it is a position 0. So the cluster number is 0. And then Y1 is 1, so the cluster number is 1, okay, and Y2 is equal to 1, so the cluster number is 2, okay? And this Y3 is 1, so cluster number is 3, and this is 2, and so on. Okay? And now I'm going to hit the Enter key, so the graphics mode will be used. Okay, so you can see that this window is created. Now I click on the screen. Randomly, this point, create some points. Okay, just randomly. Okay, and now I press the key M, so it does the clusters again, and I press the key D to display all the clusters. Okay, so these are the cluster centers, okay, or the centroids. And these are the cluster points, okay? Red, okay, green, blue, and black, okay? Yeah, corresponding to these cluster numbers. Okay. I can add more points to it. Just randomly. Okay, and I do the use MLP again. Okay, and display the results. Okay, so again you can see that these points are clustered correctly. Okay, the red, green, okay, blue and black, okay, these are the centroids. Okay. So you can try this program yourself. Okay. And thank you for watching. Okay. If you think that this video is helpful to you, please give it a like. Thank you for watching. See you next time.